Good day, class. In this video, we will continue the program of our Jacobian Matrix. Now we will program it in our graphical user interface. So we will add it in our existing graphical user interface of forward and inverse kinematics or our SCARA V3 design calculator. So instead of adding a button for our Jacobian matrix, I just added new window, okay, in this SCARA V3 design calculator. So to access that new window, I need to fill out the linked lengths and the joint variables of our calculator. Okay. Then if when I click the forward button, okay, with the with the appearance of the model, the velocity calculator will also appear. Now in this velocity calculator, okay, you will not see the velocity equation or the velocity differential equation rather, as well as the Jacobian matrix itself. What you will see here is the slider button of the d1 prime, theta 2 prime, and theta 3 prime, as well as the entry boxes of the x prime, y prime, z prime, omega x, omega y, and omega z, as well their units. Okay, so what I did here is that you can set whatever velocity you want, okay, for the d1 prime, theta 2 prime, and theta 3 prime. So example, I will set it in 30 centimeters per second for d1 prime, 2 radian per second for theta 2 prime, and 1 second for theta 3 prime. Then I will click update. So you will see here that that from differential equations, from the velocity differential equations, now it will give you the uh, real value, okay, of the differential equations or the numerical value of the differential equations with signs, okay, the negative signs. So this is what you will see in a real robot graphical user interface instead of uh, differential equation display. Okay, so to code this, we will insert our Jacobian matrix code or program to the forward kinematics function. Okay, so every time I click the forward button, this will appear, the velocity calculator, because we use to obtain the Jacobian matrix, we use the program of forward kinematics or from fkin.py. Okay, so we will do it also here at SCARA V3 design calculator. Okay, so I'm programming it to other programming it from the other folder. Okay, so let's go to the GUI.py. So at the GUI.py, we will not add another library. What we will do first is to go at the function of forward kinematics. Okay. So what we will do first, so remember, do this first. Remove the divided by 100 from the link lengths. Okay, move the divided by 100 from the link lengths. Then go to the model program. Okay, from the create links program. Then we will put here the divided by 100. Okay, put here the divided by 100, E3 divided by 100, E4 divided by 100. Okay. Also at the np.array, so d1 over 100. So let's save it. Okay. So now from this point, from the link lengths, okay, from the a1 underscore e dot get link lengths up to the ze dot insert, okay, up to this point, they are all in centimeters. So we will just centimeters instead of meter in the Jacobian Matrix program. Okay. So from the last line of the forward kinematics of the position vector from the forward kinematics, okay, we will put here the Jacobian Matrix program. The Jacobian Matrix program. Okay. So it is before the create links program or the create links code. Okay. So don't put it after the create links code. You will put it before the create links code. So again, remove the divided by 100 from the link lengths and joint variable d1. Put it at the create links program or code. Okay. As well as in the Q1 np.array. Then before the create links program, put the Jacobian matrix program. Okay, from here, we will create the new window, the Jacobian window. Jacobian window. So to create a new window, create a new variable, and we will use the code top level. So using the top level code, a new window will pop out or pop up from the original window. Okay. So we will give title to this new window. We'll call it the velocity calculator. Next is we will also make it we also use resizable, but both are false, just like the original window. I don't want it to increase its uh, length and width. Okay, from here, let's go to our Jacob.py and copy from the linear translation vector. So number one linear translation vectors. Copy it or drag it first until the j is equals to np.concatenate. Okay, copy that until that line. Then go back to graphical user interface.py. Then paste it. Okay, so make sure it is indented. Okay, it's indented within the function of F of the forward kinematics. Okay, so let's make this indented. Next. Oops. Oops. Indent. Dent. Dent. Indent. Dent. 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 Okay. Okay, next. So let's make sure that our J is a matrix with that matrix J. Okay. So again from the number one linear or translation vector, so copy it and paste it here at the graphical user interface.py until the j, okay, until the line of j variable, then add the gnp.matrix. Okay, so from here, let's enter. Then let's create a function. We will define a function. We will name it update underscore velo or velocity. Okay, so this function within the function, we will use it to to create the slider. Sorry, to update the slider every time we slide or change the slider button. It will update. Okay, so create a variable named d1p is equals to d1 slider dot get. So this will capture the value from the slider. Our slider is d1 slider. We will create that d1 slider later. So this d1p will become t2p, and this is t3p. So sorry. This is T2 slicer and this is T3 slider. Okay. Then next is we'll create a variable q and we will make it this an array. Then let's create a vector. Okay. So this vector is the joint velocity vector. D1p, T2p, and T3p are the joint velocity vector. So this is D1p, T2p, T2p, and T3p. Then another variable which is the the and the vector velocity vector. We will dot product them. The J, the Jacobian matrix, and the Q. Next, we will extract the we will extract the rows from the end effector velocity vector. So the variable for that is xp underscore e is equals to e and 0. Then this x underscore that this x underscore entry will be the variable of our entry box later. Then this is uh, the code to erase the original the old value. Then if we compute another value, the new value will be inserted. Okay, so this is x entry dot insert 0. Then we will use the code str. Okay, when we enter the code, or when we enter the value of e, or the row of e to our program. Sorry, this is to our entry box. Sorry, so this is 0 0 because it is the first row. Now let me copy this and paste 5 times. Okay, so 1 2 3 4 5 6. Now let's change this to y. This is y. This is y. This is y. Next, this is z. This is z. This is z. This is z. Okay, next. Let's borrow the omega from Jacob.py. We will not use SymPy in our graphical user interface. Okay, so this is omega x. Okay, omega x. Then this is omega x. So this is also omega x. This is omega y, omega y, omega y, and omega y. This will become omega z, omega z, omega z, and omega z. Okay. Then let's not forget that uh, the code of our slice, our extraction, should be different from each other. So these are the 6 rows of our end effector velocity vector E. Okay. Then from this function, we will exit from the function of update velo. So that's an indent. We will not exit at the function of f underscore, sorry, of yes, f underscore k. We just left the function of update velo to create these sliders. We will create the sliders here. Jacobian sliders. So this is the label of the slider. So J score SW text is equals to D1 prime false. Then font is equals to 5. Next, so the slider, the variable of the slider, then it will become, the code is scale. Then the limit, the lower and upper limit of our slider. So from 0, let's start from 0, comma, to the upper limit 30. So this is 0 centimeter to sorry, this is from 0 centimeter per second to 30 centimeters per second. So we will assign the velocity, okay, of our joint variables. So for D1 prime, our assignment is from 0 to 30 centimeters per second. Okay. So the orientation is horizontal. So it should be capital, not lowercase. Next, length equals to 100. So this will be the length of our slider switch. Next, let's create the unit. So the unit is in centimeters per second. It's W text centimeter per second. Font is equals to 5. So let's just copy this. Paste them 2 times. Let's change them into T2. T2. So this is, so instead of T2 prime, let's borrow the theta, symbol theta. Yes, the symbol theta from Jacob.py. So this is theta 2 prime. Next, the slider is theta slider. So our scale is from 0 to 3.1416. Okay. So instead of degrees per second, it will, our unit is radian per second, because if we substitute the angle into our velocities, it should be in radian. So our scale is from 0 to 3.1416, or 0 to 180 degrees degrees per second. So this is 0 to 3.1416 radian per second. So the length is also 100. We will also put slider length. So this is the length of slider itself. Slider length is equals to 10. Okay. Next, so this is radian per second. This is T2. Now this is a T3. This is a theta 3 prime. T3 slider. Again, 3.1416. 0.1416. Slider length. 83 unit. And this is radian per second. Okay. Next is the entries and labels, or entry box and labels. Entry boxes rather. Jacobian entries and labels. Okay. So first is the sorry, I forgot to put the grid command, okay, for our sliders. So for D1 velo, so that grid, so it should be it is the first label of the window. So row 0, column 0. Next, D1 slider dot grid row 1, column 0, column 0, and D1 underscore unit dot dot grid row 0, sorry, should be row 0, column 1. And this is row 0, column was 2. Okay, so this is the grid commands for the D1's D1 sliders and labels. Let's copy and paste them two times. So this is T2, T2, and T2. So these are at row 1, 1, and 1. Then T3, T3, 2, 2, 2. Okay. Now let's create the entry boxes of our uh, of our x prime, y prime, z prime, omega x, omega y, and omega z. So this is quite long. So x velo equals to label j score sw text equals to x prime, then font is equals to 5. X n3 is equals to n3. So this is the entry box. JSW, the width is equals to 10, and the font is equals to 10. Next is the X unit is equals to label JSW text is equals to centimeter per seconds. Now the font is equals 5. Okay. So these are the code for the labels, entry boxes, and units. So let's do the grid command. So x velo dot grid row equals 3. So we are now at the fourth row. Column is equals to 0. X score entry dot grid row 3 column is equals to 1, and X unit dot grid row is equals to 3 column is equals to 2. Okay, so this is Jacobian entries and labels. Let's copy this and paste it 5 times. Okay, 1, 2, 3, 4, 5. Let's change the variable. So this is y. So y prime, y, y unit. Okay. Now this is now at row 4. Next, z. Entry, z unit, z, and z. So this is now at row 5. Okay. Next, we will use the omega symbol here. May I borrow the omega symbol? Okay, so this is omega x velo. So because omega x, okay, omega x, omega x, omega x, omega x, omega x. Sorry, wrong, wrong. Copy this. Okay. So this is let's put omega. Oh, sorry, wrong. See, this is uh, omega. Omega. Let's change them into y. So this is omega y. Y Y, then sorry, I forgot to change this. This is row 6, row 6, row 6, then I go Y. Okay, the unit is now radian per second. Y and omega Y. Okay, so this is row 7, 7, 7. Next, okay, last but not the least, the omega Z. Okay, let's put omega Z here. Then this is rad per second. Then this is 8. This is 8. This is 8. Okay. Then after the label and entries, we will create the update button. Update button is the button that will update or solve the the velocities of the end effector velocities. So we will create a new uh, a new variable update but so this is a button, then j underscore sw text. So the text is update. Sorry, it's now outside. Next is I want the color of the button is green. I want also my font. Yeah. I want my font white. Then at the last, okay, we will put here the command and we will put the update value from the defined function earlier. Then we will create now the dot grid command. So we will put it at row 9, column 0. Okay. So this is the program of the forward kinematics in our graphical user interface. So again, after the z underscore e dot insert, we will put the Jacobian Matrix program. We will copy. We will create first the window. This is a pop out or pop up window. Okay. Next, the linear translation vectors and the rotation vectors. Then the concatenated Jacobian matrix. Then the velocity. So this is the velocity slide update. Slide update. Okay, so it is a defined function. Okay, then out from the defined function are the the Jacobian sliders, then the Jacobian entries and labels for the for the entry boxes and for their units, then the update button. So we will now test this in our terminal. So we will go back. Okay. So this is our SCARA V3 design calculator. If we click the forward, the Jacobian matrix should appear, but we need to put some values first for our link lengths and joint variables. So we will try A1 is equals to 20, A2 is equals to 30, A3 is equals to 10. Oh, let's try first our first example from the Jacobian matrix or Jacob.py. Uh, Jacob.py program. So A1 is equals to 55, A2 is 60, A3 is 30, A4 is 60, then D1 is 100, T2 is 0, T3 is 0. Then I will click forward. So this is the model. So let's close it first. So this is the velocity calculator. Okay. So if you click the update, so there will be no value. Oh, sorry. I think there is something wrong. From 1 to 3 positional arguments, but 3 were given. So I think this is wrong. np.array. Let's try to put some values. Sorry. Let's make it this 6. This is 1. Okay, there is something wrong. There is something wrong in the program. Oh, I forgot. This is a vector. So let's go back to that queue. This is a vector, so it should have square parentheses outside. Okay. Let's let's test again. If you close this, the velocity calculator will close also. This is the velocity calculator from the from the original code. So let me close that first. So let's check again. So again 55, 60, 30, 60, and 100, then 0 and 0. Click forward. Okay, so this is the velocity calculator. If we click update, okay, there are zeros at our in our entry boxes. So there are no errors. So let's proceed from so let's see if what is the what is the velocity if the D1 prime is 30 centimeters per second. So let's update. Okay. So based from our let's use this. Okay, based from our program at the Jacobian Matrix. Okay. This is the differential equations. Okay. According to this, z prime is equals to d1 prime. Okay. So if we analyze this, z prime is equals to whatever d1 prime is. So d1 prime is 30 centimeters per second. So let's test omega z. It's equals to 1. Then click update. So omega z is equals to 1 according uh, to our Jacobian Matrix from the program of Jacobian Matrix. Omega z is equals to theta 2 prime plus theta 3 prime. I if I make theta 2 prime 1, so omega z is equals to 2, the sum of theta 2 prime and theta 3 prime. While omega y is now changing, so omega y prime according here is 120 theta 2 prime plus 60 theta 3 prime. So because theta 2 prime is 1 radian per second and theta 3 prime is 1 radian per second. So 120 plus 60 is equals to 180. So as you can see, this is correct. Okay. So we can change or we can set the velocity or we can calculate the velocity in this velocity calculator. We can also use this to analyze the link length of our mechanical manipulator. If the length of our link length changes uh, the velocity of our mechanical manipulator. So let's see if we make this at 30. Then this is 30. This is 30. This is uh, 10. Then this is 15. Okay, let's make this 5. 90. Then negative 45. So let's click forward. Wait a minute. Why XYZ is too big? Right, XYZ is too big. Oh, I forgot to remove the sorry. You should remove also the times 100. You should also remove the times 100 at the position vectors. Okay? So that's why the value is too big. Okay? So where is that? Okay, this one. So as you can see, we can also uh, create additional velocity calculators. So let's update. So let's see if it is 30 centimeters per second. So it's 30 centimeters per second. Still. Okay, so omega z is 2 because 1 plus 1 is equals to 2. Then as you can see, when we put some values for theta 2 and theta 3, okay, the x has a value is negative 51 and it's very fast. Okay, at the direction of x-axis, at the direction of x-axis, it's very fast going to the left. Okay, or going to the negative side. While y at the direction of y, it is slower. At the direction of z, it is also faster. Okay, so it will depend in our calculation here. Okay, so we are utilizing the slider. We are not just typing the value, but we are also using this slider. Okay, so this is velocity calculator. Uh, Again, don't forget to remove the times 100 from the position vector. Okay. So I already removed it. Let's check again. Okay. So this is 20, this is 30, this is 10, this is 15. Let's put some 100. Sorry, not 100. Let's put 5. This is 30. This is negative 45. Click forward. Okay, it's smaller now. And also, you can see here. Okay, so it's still 30. Okay. Oh, y-axis is now faster. Okay, y-axis is now, it is faster now at y-axis. So, the, I think the joint variables are based from this simulation. If the joint variables also affect how fast our end effector at x direction, y direction, z direction, and x, y, and z axis. Okay? So you can analyze the the velocity of your mechanical manipulator using this velocity calculator. Okay, so this class is the part 2 of the Jacobian Matrix program. So I programmed it at inside the graphical user interface. I just added a new window that will pop up or pop out after pressing again the forward kinematics. Okay, so I hope you get this. So thank you.